Voltage drop issues on a PCB can be easily identified using power integrity analysis. All the power nets can be examined for voltage drop issues based on expected current draws. Then analysis results are presented in both graphical and report form, allowing you to quickly pinpoint problem areas in the design. You can find out precisely if certain areas require more stitching vias or more copper to meet your current demands. So let's take a quick look at how to analyse potential voltage drop issues using power integrity analysis. You can analyse all of the power nets on the board using batch analysis or analyse individual nets interactively. For example, let's take a look at the 1.5 volt power net on this board. I will highlight the net so I can see the plane shape in the board viewer. Now that I am ready to start the DC drop simulation, I can select from any power net on the board. Here is the 1.5 volt net, where I have already assigned the VRM and current draw numbers to the ICs. I can now go ahead and launch the simulation, which may typically take a few minutes to run. After the simulation is complete, I can use the report and the power scope to review the results. In power scope, I look at the results in 2 and 3 dimensions. In this 3D plot of voltage drop, I can add a threshold plane to see if any areas of the power plane fall below my target value. In this case, I am targeting less than a 5% voltage drop, so I have a threshold plane at 1.425 volts. Clearly the lower part of the plane is below the required voltage. Reviewing the voltage drop in 2 dimensions, where colour indicates the voltage level, everything coloured red is below the target voltage level. I can also look at DC current density. Adjusting the scale allows us to see the hotspots on the board. That is, areas of high current density that could lead to heating up of the board and/or voltage drop issues. On this plane, these hotspots are at the neck down between the upper and lower portions of the plane and the via feeding the plane. The high current density in these areas can be greatly reduced. I could add additional vias feeding the plane, as well as adding more copper to connect the upper and lower sections of the plane. I can also view the results in the summary report. The report lists the current and voltage at every pin and via on the power net, with a summary of the worst case conditions at the bottom of the report. All of the coordinates and pin listings in the report are hyperlinked, and clicking on them highlight the appropriate location in the board viewer. This allows you to quickly identify areas in the layout that need to be modified in order to minimise areas of current density, minimise voltage drop across the planes, and meet the current demands of your power-hungry ICs. You've now seen how power integrity analysis takes the guesswork out of beefing up your power planes and traces, enabling you to pinpoint and eliminate voltage drop issues before you even build your first prototype.